The next part, chapter 10 and a bit of 12. Previous one was chapter 11 and a bit of 12. Okay, so this one is all about gases and first law of thermodynamics. So I think what I'll do is I'll bring in the mind map again. But there we go. Okay. Oops. So for chapter 12, right, we started off with gases. And when it comes to gases, there are two types of views, remember? We have the macro view, meaning we look at the sample. Maybe a balloon got gas inside, maybe a flask with gas inside. And when it is macroscopic, we can measure the physical quantities like pressure, volume, temperature. Okay, so whenever it's macro scale, right, macroscopic, the questions are very easy one because we are using the ideal gas relationship. PV is equal to nRT. So PV is equal to nRT or PV is equal to NKT, this part here. So, but the problem here is that this question is very rarely a standalone question. Meaning to say, it's very rare that they just ask you to find the temperature with a given quantity. They need you to provide something else. Okay, so I will show you what I mean by a question very soon. Then we're going to move on to the microscopic scale, meaning we will zoom in on the gas and then think about the little particles. So if you look at this side of the equation, this second equation is given in your exam paper. That is the only equation that they give from this chapter. Okay, but this Nm is the number of particles and this m is the mass of one particle. So essentially what we're doing is we're taking the mass of the whole sample divided by volume. Okay, so we can use this format. We can also use this format, density. I asked this question in trials. Okay, so based on this, we have successfully linked what we cannot see, which is the mass and the dimensions of the particle, to what we can see and measure, which is the pressure and the volume. So we started off with a particle in a box to derive this equation. So this particle in the box one, where we have this particle colliding with the wall of the box, there's a proof here that they kind of sometimes will ask, but it's not very popular. What is more important is you know how to use these equations and you know how to derive the equation from half rho c square to this internal energy 3/2 kT. So I'm going to show the derivation or summarize the mind map even more. But let me zoom out a bit first so that it's okay territory. All right, so I'm going to start off with the first one. You need to know ideal gas. PV is nRT, PV is NKT. Auxiliary equation, you should know the mole concept. Yesterday, we talked about the mole concept when we talk about nuclear physics. Same thing here, same concept. But the mole concept is even more important. So K is equal to R over Avogadro constant. R is the universal gas constant. Numbers you can find in the table. All right, make sure everything is SI. SI units only. Second equation you have to know how to use is PV is equal to 1/3 rho c square. No, P is 1/3 rho c square. This one is given in your question paper. Let me find question paper. It is given. There we go. But it is given to you in this format. They are the same thing. This Nm is mass. Total mass. Mass of the gas sample. And then this V is volume. Mass over volume is density. Okay. What is C square? C square here is your mean square speed. Mean, the bracket is mean ma. The power 2 is square ma. Speeds. All right. So what we need to do is we actually need to derive some stuff lah. So I will quickly show you the derivation because they are fast. So you should be able to do it. So step 1, you see this PV is equal to 1 over 3 NMC square. Right? Step 2, you see PV is NKT or NRT. Let's use NKT lah. If you don't know, this N is number of moles. Small n, number of moles. Capital N, number of particles. Okay, so equate them lor. 1 over 3 NMC square is equal to NKT. Can chop the N? Can. So you have 1/3 MC square thing is equal to KT. MC square is equal to 3 KT. How to find kinetic energy again? Half MC square, right? You multiply by half both sides, 3 over 2 KT. So this is the third equation. Sometimes they will ask you to prove, and I think this proof is quite worth it lah. Normally it's 3 marks one. Very nice. You just write this equation and you write this equation you can copy ma. You see it's the same equation. This one you don't know, maybe defer physics. Maybe just don't answer the question. Okay, so you just equate the equation and then you just multiply by half. Yeah, you can one. I believe in you. You believe in yourself or not? So EK is equal to this one. So finally we have kinetic energy is 3 over 2 KT. This one. Okay, so it's the third equation that you need to know. Kinetic energy is 3 over 2 KT, but you can break it down, okay? So from here, I can find the mean square speed. Mean square speed will be 3 over 2 KT. The over 2 will go away. So it's 3 KT over M. From here, so no. Beware, be warned. This M is mass of one particle. You may need to use the mole concept to find the mass of one particle. Red alert, mole concept. You want to answer this chapter, make sure you and the mole are friends. Like some secret agent. Okay? If they want root mean square, you square root this one, okay? Root means you add a square root. And you square root the answer lah. Note. Gas, RMS gas speed. This one can be from few hundred to few thousand. Please, if you didn't convert your unit, your gas speed will either be super fast, like faster than the speed of light, which is wrong, or super slow, like 4.0 times 10 power negative 8. If the gas particle moves so slow, we suffocate and die lor. The gas cannot enter your lungs. Okay, so a few hundred to a few thousand meter per second. This is a good hint to whether you will calculate correctly or wrongly. Or you didn't convert units correctly. You substitute the wrong constant. I don't know how students can choose the wrong constant from the table one. Did they give you K? Got there? So I think maybe you forget lah. Nah. It's this one. It's called the Boltzmann. Boltzmann. See, all the gas is together in one place. You need molar gas constant, which is R, Avogadro constant, which is the number of particles in 1 mole, and the Boltzmann constant, which is R divided by Na. I put here again. See more, remember more, right? Less mistake. Yes, you got this. So this K, R divided by Na is equal to K. See, they put like this. Try to help you. Did it help? Not sure. Do you notice? I don't know. Okay. So this is the part where some students will get lost in translation because they either are not familiar with PV is equal to nRT and nKT, or they don't know how to use these equations because they don't understand that we are now looking at the gas particle, zoom in and look at the microscopic. Okay, so this is the kinetic energy. The fourth one would be internal energy. For ideal gas, internal energy is 0. Internal energy is 0. Internal energy is equal to Ke. But if you want to define, internal energy is Ke and Pe, and make sure you talk about the random distribution of gas motion. Distribution. Okay, so internal energy of the gas. So it's a sum of the random distribution of Ke and Pe of gas particles. Okay, but for ideal gas, what is 0? Pe is 0. There are no intermolecular forces. So make sure if they ask the assumption of kinetic theory, you are okay lah. No intermolecular forces. All collisions are elastic. So Pe is 0. So hence the internal energy is only equal to Ke. But Ke is 3 over 2 kT. This 3 over 2 kT is for CBG 1 particle. Means if many particles in the gas sample, then you multiply by n, no? Ek would be 3 over 2 nKT. This is for n particles. Make sense? Later we do a question. All right. So this is 3 over 2 kT for a single particle, or 3 over 2 nKT. But the most important thing here is kinetic energy is proportional to temperature. And when we reached this point as a student, I was very happy. Because since primary school, my teacher has been telling me, you heat up the particle, you heat up your eraser, you heat up your fry egg, the little molecule and atom in the egg will begin to vibrate more vigorously. And I'm like, sus. How you know the particle vibrate more vigorously? Can we tell? Can we show? Can we derive the equation? Now derive for you already. Kinetic energy is proportional to temperature. Even if there's potential energy, when you change the kinetic energy, you change the temperature, you change the whole energy of the substance. Sometimes you change the state, sometimes by weakening the bond or severing the bond, breaking the bond. Sometimes you will change the vibration by increasing the temperature. So this is what happens when we zoom in, when we heat up the water, or when I put ice in my coffee. All right. So anything else that I'm missing out on? Yes, your good friend, number 5. So all this is us together in any combo that they like, which is first law of thermodynamics. Which is the change in internal energy is equal to heat added plus work done on or by the gas. In order to use the equation, you have to know the sign convention. Let's go through the sign convention and see if we have our head on straight. Q, okay, I'll start with delta U first. Delta U, Q, and W. Can be positive, can be negative. The easiest one is Q. Positive when heat is added, negative when heat is removed, 0 when there is no heat flow. Make sense? Okay. Delta U. You see this delta U is directly proportional to temperature. So delta U is positive if U increase, and U increase if temperature increase. Delta U, or change in internal energy, is, actually this is U. Delta U. Delta U here, you need delta T. Okay, so U will decrease if temperature decrease. And for physics, we always talk about change one. No, always this one change, that one change, ask you to calculate this, calculate that. So to know whether the internal energy change or not, just look at temperature. My friend, we can add heat and still decrease the internal energy, okay? Possible one, because there's still W. For W, it's a bit different. W here, if it's positive, means you add energy to the gas. So volume decrease. This one, volume increase. Okay, so gas is compressed. We add energy to gas. Work done on gas. Okay, this one, gas expands. Work done by gas. And you want to find this W. W is equal to P, change in volume. This is from your AS, change in volume, at constant pressure. So if I look at this question, right? This delta U, it can be pulled into EK is equal to 3/2 NKT. And then from here, I can relate this to mean square speed. Right? So this one is one way of asking. This Q can be pulled using MC delta theta. This W can be P delta V. Meaning to say, this equation is KL central. Can travel to many locations or can come from many places. We can insert first law of thermodynamics into many parts of this story. PV is nRT, NKT, the rho C square, all these can. You see the connection, you can adjust accordingly. Number 2, questions that they can ask. The first type is calculation involving calculation with this one, and this one. So 1, 2, 3. Using the link 1, 2, and 3. Any combination they like lah. You don't know one lah. Because if I can hear rho C square, you see this P delta V. This P delta V is macro one. So can use PV is nRT. They're all gases ma. Second type of question is gas cycle with your PV graph. Third type of question is explain using first law. You can see why they prefer to ask this, because it's like choose your own pizza. You know, you can choose your own topping. Do you want to ask this side? Do you want to ask this side? Ask this side? Ask student to explain. Ask students to stare at the graph. Okay, so I will probably do some from each group. If you have any requests, those of you who are joining the recording session, Laila, which one you think is the most challenging one? I will do some now. I guess I'm going to start with I will do the 2020 variants. So I'm going to start with the FM20. Question 2. No, even if you cannot complete the question, there are some easy parts one. Then you see whether you can figure out which link they are talking about. Okay, so ta-da! Wow, why so big one? Okay. So here we have a large container of volume 85 meter cube filled with 110 kg of ideal gas. Well, this is a very big container, bro. Pressure of the gas is 1.0 times 10 to the power of 5 at temperature T. The mass of 1 mole of gas is 32 grams. Show that the temperature of the gas is approximately 300 Kelvin. Okay, everything here is macro. Can measure. I know what volume 85 meter cube is. I'm not talking about like the particles moving. So we're going to obviously use PV is nRT. Problem. Let's see what we have. We have V. We have mass, which is meh, not needed. We have P. Okay, we want to look for T, so can. But we don't have N. So we need to find N first using the mole concept. So we can use mole concept is actually ratio. 1 mole is 32 gram. 110 kg is N mole. Can you find N? Can, right? N will be equal to 110 kg times 10 to the power of 3 gram divided by 32 gram. You scared make mistake, you calculate at the side, no? 110 power 3 divided by 32. So our friend here is many moles, 3437.5 moles of gas inside this 85 meter cube container. Okay, we can substitute now. Pressure is 1.0 times 10 to the power of 5. Volume is 85 meter cube. Number of moles is 3437.5. R is 8.31. Please show the substitution. Then you can find your temperature. If you don't show your substitution, you'll probably lose marks as well. Because I'm going to open up the mark scheme and see what substitution you're required to show. Okay. So as expected, if you have this, you get C1. If you state the equation PV is nRT, you get C1. And then this one leading to 300. Do I get 300? Let's see. 1E5 times 85. I get 297.56. 297.56, so 297.6 now. So around 300 Kelvin. So the substitution is 1 mark. This is bonus, guys. It's a very nice bonus. Don't let it go. Okay. Let's move on to the next part, which is part B and C. So for this part, you are given that the temperature of the gas is now increased to 350 Kelvin at constant volume. Whenever something is constant, from the perspective of the gas, this is very important because we can decide what is happening in your P, your delta V, and your temperature. Specific heat capacity C of the gas is this much. Calculate the energy supplied to the gas by heating. So I want to know what is Q. Okay, so you're going to start off with the first law of thermodynamics. Delta U, change in internal energy, is Q plus W. Okay, my friend, constant volume, W is 0. There is no work done if the volume is constant. Okay, so then the change in internal energy will be equal to Q. We have a few choices here, right? We can continue this part. So this is 3/2 NKT because we have many particles, not just one particle. But NKT is also nRT, what? We have the number of moles there. Nah, PV is nRT. PV is also NKT. So these two, nRT, NKT is interchangeable one. So we could substitute this. 3/2, the number of moles is 3437.5. This is 8.31. And the change in internal energy is due to the change in temperature. So 350 minus 50. Mm-hmm. 0.5, 3437.5, 8.31 times 50. Increase to this much at constant volume. Okay, so if you do this, you'll get 2.14123456 times 10 to the power of 6. Lots of energy. But you didn't use this specific heat capacity. So on the other hand, you are wondering, can I use MC delta theta? So we have 110 kg of gas. This C is 0.66. The change in temperature is 350 minus 300 Kelvin. And this one will obviously not give you the same answer. This is 3630. So which one is it? Let's pause a while and think. Obviously, someone is wrong, left and right. What is going on? Okay, so the answer to that is, if you look at this one, you don't have enough information about the state change. Okay, so when you use this question, is all the heat used to change the internal energy? Don't know. Is this gas, I mean, we are assuming it's ideal because we use PV is nRT. So it is unknown that whether all of this is it used to increase KE only? Is there state change? Don't know. It may seem that there is none, but the thing is there is not enough information. So always whenever you do this, right, a double check and default to the more simpler one, which is this one. Because sometimes CIE, when they set questions, right, you have to think from the perspective of the examiner. What information are they giving you? And what are they trying to confirm or deny? And then the second thing is, if it's a constant volume, the pressure will increase, right? So where did that energy go? Okay, so only use first law when it's like very obvious, when they talk about how many joule of energy is added to the system, then can. All right, so I'm gonna continue this one. 3630. This one is wrong. Put question mark. Next, here so many lines. One, explain how the movement of the gas molecule causes the pressure in the container. This is pretty easy then. This one looks like a secondary school science question. So the reason why there is gas pressure is because the gas molecules collides with the wall of the container. Okay, and then what happens? Think about the particle in the box. Momentum of the gas particle or the gas molecule changes during collision with the wall. There is a force on the gas molecule by the wall. Hence, there is also a force on the wall by gas molecule. Who say one? Newton law. Newton is everywhere. So then you extend this to all the gas particles. There are many gas particles. Hence, many forces are acting at the same time over the surface area of the container. Exerting pressure. There are 4 points here. 1 point is 1 mark. You can get up to 3. So gas molecule, imagine this is your box, right? The gas molecule will collide with the box. Whenever there is a collision, the gas molecule here will experience a force causing it to change direction, meaning the wall will push the gas particle away. Force on gas. But from Newton's second law, there has to be, second law, third law, there will be a force on the wall. And there are so many particles, ma. So pressure is equal to force on the wall divided by area. So the gas molecule colliding with the wall of the container is 1 mark. Okay, momentum of the gas molecule will change is 1 mark. And because there's a change in momentum, there is a force on the gas molecule by the wall. So there's also a force on the wall by the gas molecule, 1 mark. So because there are many particles, so many force will act on the entire box. Push, push, push. Everybody push. Billions and billions of gas particles is pushing on the walls of the container, 1 mark. I feel like this is something they put so that to see whether the candidates know their sciences or not. Okay, so we talk about this when we derive the mean square speed equation, which brings us to the last part of the question, which is this mean square speed one. So temperature of the gas depends on the RMS speed of the molecule. So if you want to find RMS speed at 350 and 300, I'm just going to write the equation first. This one is 3/2 kT. So C square is proportional to temperature. Okay, but RMS, which is root mean square, is proportional to square root of T. So then you can say hence the ratio that they are looking for is equal to square root of 350 over square root of 300. And then you press your calculator. 350 over 300 square root. Don't leave your answer like that. We will cry. So don't leave your answer like this. Hello. AS already mentioned no ratio, so this one cannot lah. So this will be 1.08 2 to 3 SF, especially when it comes to ratio. Okay, let's look at the chat. Okay, so carrying on, where we are there. So it's not hard one, it's just because you know practice and then the equations are a bit weird. So need a bit of a warm up to do it. Okay, answer is 1 mark. And also the proportionality relationship, this one is 1 mark. So the idea that you know that mean square speed is proportional to temperature or root mean square speed is proportional to square root of T. Please remember the square root lah. That's the question. Not much for this one. It's pretty straightforward. I'm going to move on to the next type of question from summer 20. So for summer 20, is full on explain. I miss explain. Yeah, lor. So I will quickly explain. But I think this one is actually easy because you have a framework to explain. So it's not like I'm asking you to explain and think of something different. So let's look at this one. This is, let me write down the year first. Summer 20 or May-June 20 paper 4.2, question 3. Asked this in your trials before. So different scenario. Using the first law of thermodynamics, state and explain the changes, if any, in the internal energy of a lump of solid lead as it melts at constant temperature. Trial, I asked melting ice. Now they ask melting lead. Okay. Some gas in a toy balloon bursts. And some more, they're so helpful No thermal energy enter or leave the gas. Okay, so you can see, although they try to change the question, there's not much they can change because the scenarios are more or less the same, right? So whenever you want to write this, write the equation first lah. Delta U is Q plus W. So you need to explain internal energy, the change in internal energy. So I need to mention Q first, what changes for Q, what changes for W, and then conclude. So they say you want to melt the lead. Heat is absorbed to weaken bonds as lead melts. Means constant temperature, I know, but the bond weaken potential energy increase. Here got state change. Okay. W leh? W here, I don't think when solid lead melt, there's much change in volume lah. So I will just say change in volume, negligible. Work done is 0 or no work done by lead or on the lead is 0. So if Q is positive and W is 0, so what happens to your delta U? Positive also. So because of this, internal energy of the gas increases. Q is equal to W plus delta U. So normally if I'm a student, I will write like this first and then I will erase this part pencil ma. You leave it here, it doesn't matter. Okay. This gas in toy balloon one is identical to trial. So hopefully you've watched the discussion, but you can repeat the same procedure again. Q, W, delta U. Okay, I will write in more brief format. No thermal energy enter or leave. So Q is 0. Because no thermal energy enter or leave. W, gas expands right? Because you burst the balloon. So gas expands rapidly. Volume increase. Work done by gas. W is gas do the work, so the gas energy will be less. So it's negative W. Okay. So Q is 0, W is negative, so delta U must be negative, right? So then you can say internal energy of gas decreases. I will show you the mark scheme now. Question 3. So I haven't seen the mark scheme in my life. So now we compare them side by side lah. So little to no volume change, so no external work done. Yay, 1 mark. Thermal energy supplied to provide latent heat. Weaken the bonds as the lead melt is the same thing. Okay, or since they... So now I'm going to upgrade my answer to supply or to provide latent heat. Whenever we have latent heat, here is for state change one, which have the same meaning as weaken the bonds. So you have to mention why the heat is being absorbed. So this is B1. Internal energy increase. Yay. Rapid increase in volume. Work done by gas. So if work done by gas, they want me to write against atmosphere. That would be more complete. Okay. Then the internal energy decreases. So this part here, no mark lah, because they already mentioned, so they took away the mark from you. So maybe 5 out of 6 or 6 out of 6, depending on how lenient the examiner is lah. Okay. So work done by the gas against the atmosphere. But when you see by, it's understood that it's against something. So this English term. So that is the variant 4.2. Let's look at variant 4.1. MJ20 P41. This one also a bunch of explains, but it's also about 6. So this is 7 marks. So sometimes you study this chapter so 辛苦, so difficult, so brain pain, and then they just ask like this kind of 7-mark question, a bit sad. This is what I mean by maybe it's not. Maybe this is the kind of chapter where you should spend a proportional amount of time lah. Okay, so state what is meant by internal energy of a system. This one would be the sum of random distribution of KE and TE. Asked before in trial already. So if you come out, you just write the answer. Okay, to save us some time, I am going to. Okay, so total potential energy and kinetic energy of the molecules and atom refer to the random motion. Must be here. So I will just say something along the line of random, the sum of the random distribution of kinetic and potential energy of your atoms and molecules. In fact, you can even just period and then go like atoms and molecules are moving in random motion. Can. By reference to intermolecular forces, explain why the change in internal energy of an ideal gas is equal to the change in total kinetic energy. So they're asking you why delta U is equal to KE. Because PE is 0. So internal energy is supposed to be KE plus PE. But for ideal gas, PE is 0. And the reason why PE is 0 is because there is no intermolecular forces. Okay, so you can say in the ideal gas, there are no intermolecular forces. And because of this, there is no potential energy. So the change in kinetic energy is the change in internal energy. Because this one becomes 0. Also like to ask one. Okay, state and explain the change in the internal energy of a solid metal ball as it falls under gravity in a vacuum. Oh boy, what is this? Metal ball falling under gravity. So we got to go through the the Q, the W, and the delta U. Okay, question. If it's vacuum, is there friction? No friction. If it's not vacuum, you expect some form of friction. Maybe the temperature of the ball will increase because it rub against the air, right? It travel against the air, there's friction. Maybe the temperature will increase, but then there's no friction. Okay, so because of this, I can just say that there is no change in volume of the ball. So no work done. Weird question, bruh. Okay, so then use this one. You can say there's no resistive forces, no friction, no drag force, nothing on the ball in vacuum. So no heat transfer to the ball. Everybody 0, my favorite number. Hence, internal energy does not change. Because Q equals 0, W also 0. Then delta U 0, because 0 plus 0 is 0. 0. We'll explain once. Right, so that is the summer 20 papers. Finally, I will do the winter 21. The Winter 21 is quite similar to the trial paper. In the trial paper, I asked 2 guess questions. Okay. Anyway, I'm planning to set 2 model papers for you. So you prepare yourself as you revise. Then try the model paper in exam condition if you can, to see whether you are ready. Again, you don't have to, holy cow, too big. You don't have to answer the question perfectly. Okay, so there are certain chapters where it is okay to sacrifice one, you know. But make sure those that you are not sacrificing, you are okay lah. Strategy now, guys. It's time for strategy. Okay, what else do we have? This one looks like a combo. Anyway, people who are still around, you stay for so long. Thank you. Across the recording session, so I feel less alone. But I'm going to ask you, do you need me to discuss a gas cycle question? The one with the graph one. If so, let me know in the chat, okay? Okay, this one is this is ON20 paper 42. If not, then this will be the last question. But if you want me to discuss a gas cycle one, the one with the PV graph one, let me know. Okay, again, internal energy. Sum of random distribution of kinetic energy and potential energy of gas molecules. I will write better if it's the exact. Okay. The atoms of an ideal gas occupy a container. There's energy here. Sus have to use this one already. Delta U is Q plus W. All right. So we have the initial state and we have the final state. This is temperature T. Gas is heated at constant pressure, so the volume becomes this one. Okay. For the fixed mass of gas, calculate the amount of substance in mole. This is bonus. We're going to start with this one first. PV is nRT. So the gas doesn't have more or less particles. The number of particles are the same. So we are going to put in 2.30, 2.60 times 10 to the power of 5. Volume 2.30 times 10 to the power negative 3. Find number of mole 8.31. Temperature 180. Find N. This is easy. So easy. That's what all the teachers say. So if they come out, at least make sure this one you can do. Even if you decide to not really pay much attention to this chapter. This is 0.400 mole. Okay. The temperature T in Kelvin. I see constant temperature, constant something, I'm very happy one. Because I can use this instead of substituting all these prefixes. So I know that P is constant. So ideal gas is the gas that obeys the law, PV over T is constant. So if P is constant, PV over T is constant, then I can say P1 V1 over T1 is equal to P2 V2 over T2. But the P is constant and we can cross out the P. So I can take V1 over T1. V1 is 2.3 times 10 to the power of negative 3. The initial temperature is 180. We are trying to find T2. The volume here is 3.8 times 10 to the power negative 3. This is the easier way to find now. Of course, you can PV equal to nRT all over again now, but ratio is my best friend. So I'm going to use this, and I'll find T2 as 297 Kelvin. Okay, so whenever there's a change in pressure, volume, temperature, especially if they are constant, then we can use this kind of relationship. Okay, so during the change in B, because the temperature has increased, right, from 180, the delta T is 180 Kelvin to 297 Kelvin. So there's also a heat added plus Q. Determine the work done on the gas during this change. Explain your working. So W, have to explain. P delta V. Because why? Pressure constant. Okay, we have the pressure. Let's go hunt for the pressure. Pressure. 2.6 times 10 to the power of 5. So 2.6 times 10 to the power of 5. Change in volume. What's the change in volume? 3.8 minus 2.3 times 10 to the power of negative 3. This is your delta V. V1 is here. V2 is here. Minus the volume. So we can press our calculator and we will get 390 joule. But it's 3 marks. You have to think about where the marks are. Not then you lose 2 marks. So the first one is work done is P delta V, 1 mark. Substitution leading to this answer is 1 mark. Where is the other mark? There is a negative sign here, guys. And you have to explain why there's a negative sign. So you explain here. Negative due to work done by gas to expand. Against, we learned from last question, against atmosphere. Okay, and finally, determine the change in internal energy. We can use delta U is Q plus W. So Q here is 980. Supplied, so it's positive. Okay, always check the sign. W is negative 390 because the gas is expanding. So from here, you can find your delta U as 590 joule. So 1 mark, 590. That's all. Very nice one. Got 10 mark already. I think this 10 mark is nicer. Look at this. Fun fact, I set your model paper, I set your trial paper before the ON paper was out. It's very similar. So be aware that you can use this relationship, especially if only one of them change up. You can just cancel out the constant. And then just do slowly, follow the relationship. There's a gas cycle question in the other variant, but I have also set that as test 2. Test 1. So you go and review or try the ON20 paper 4.1. It's the gas cycle one. This one come out in test 1 already. So since some of you say that, okay, if you need the gas cycle question, I'll discuss now. But if you want to go off to have lunch, you just say bye in the chat. Let me go and dig out a gas question. But yeah, if you need to go, you can go. If you want to stay, you can stay. I will record one last gas cycle question for the peeps. Okay, I'm going to do... Wait, let me make sure it is not already recorded. Just to benefit everybody. Gas cycle questions. Ding, ding, ding. Okay, we have done this one. All right, we're going to do MJ19 P42. They are also quite popular. The gas question. Yes. Very popular because the graph looks very fancy, and also because the cycle of thermodynamics is a very important engineering idea. It shows the conservation of energy so beautifully, and most machines, the engineer's job is to make sure that the cycle is as efficient as possible. And I choose this question because they read all the coordinates for me, so I don't have to strain my eyes staring at the boxes. I'm old, my friends. And I mark many graphs for a living. When not needed, I would not like to stare less at graphs. Especially the one where I need to read the values. Okay, lots of story here. We'll read them together. But let me finish cropping the question first. So if I see this, I'm also quite happy as a student because it's accounting. It's like playing Sudoku, you know, just fill in the blanks. At least that's what I think. All right, this is 4 marks. Okay, so let's go. Major 19, paper 42. First law of thermodynamics may be expressed in the form of delta U is equal to Q plus W. Okay, positive Q, heat added to the system. Positive W, work done by, no wait, work done on the gas. Okay, work done on the gas. By atmosphere, by external forces. You just put added and on, your mark is on now. State what is represented by a negative value of delta U. Internal energy decrease. Temperature of the gas decreases. Okay, next. Ideal gas sealed in a container undergoes a cycle as shown in figure 2.1. Sure. And they very helpfully give you all the temperature, pressure, and volume, PV. So nice, thank you. At point A, the gas is under this condition, and the gas is compressed suddenly so that no thermal energy, okay, this is important. No thermal energy enters or leaves the gas during the compression. Okay, where is the compression? From A to B, I assume. Yes. So when you go from A to B, okay, let me zoom out a bit so we can see the whole thing. A to B is here. All the way up the curve, like that. This is A to B. Okay. So in this A to B, this yellow curve, your Q is 0. We compress the gas without removing heat or adding heat. No thermal energy enter or leave the gas during the compression. So I'm going to write here QAB is 0. Big, big. The amount of work done is 480 joule. QAB 0. WAB is 480. Wait. Chotomate. Positive or negative? Volume decrease. Gas compress. Work done on the gas. Volume decrease. This is positive. Okay. Gas has volume this much, pressure this much, and okay, this is B. This is at B. The gas is now cooled at constant volume. Okay. Constant volume means what? This feels like an English comprehension question now. Constant volume means there's no work done. So the work done between BC is 0. Right here again, no, WBC equals 0. Okay, so BC is here. British Columbia, Bahasa China. Okay, so BC is here. And you can see the volume is constant. They don't really have to tell you in a sentence one. You should be able to tell just by looking at the graph, especially this part. Okay. Between points B and C, 110 joule of thermal energy is transferred. Okay, no. QBC is 1100. Ask yourself, positive or negative? Transferred. Positive, negative? Don't know, put one side first. At point C, the gas have this pressure and this temperature. Finally, the gas returns to A. So from A to B to C to D. Okay. State and explain the total change in internal energy for one complete cycle. You return back to your initial temperature, right? You are back at your initial temperature. So the change in internal energy is a 0. Because you're back to the internal energy, the initial conditions. So total change is 0. And if you want to explain why, this is because there is no change in temperature. Okay, don't say it returned to original condition because you are not clear about what condition you are talking about. So please use temperature. So this is 1 mark. Then you say there's no change or the change is 0, 1 mark. Calculate the external work done on the gas from C to A. Okay, let's go back. C to A is this arrow. So we need to find the area under this graph. So work done from C to A will be P delta V. Do we have the pressure, my friends? Got the pressure is 1.6 times 10 to the power of 5. Change in volume, leh? See, now you know why I choose the question. I can just take the values. Okay, so we're going from 2.4 times 10 to the power negative 3 to... Let me nudge this over so I got more space. Minus 8.7 times 10 to the power of negative 4. So I pressed the calculator, I got 240. Slowly press lah. Question, positive or negative? Your volume increased from C to A. So from C to A, volume increase, W is negative. So there's a negative here. Okay, to show work done by the gas. So that will be the work done. 2 marks. Wait, I should just sapu the whole thing. Ding, ding. Okay, so this negative 240. Where are the marks? P delta V and substitution is C1 mark. Final answer is A1, including the negative. Okay, complete figure 2.2. Well, my friends, we did harvest some stuff in our inventory here, right? Can we put them in first? If you... I'm going to just drag this thing down so we can stare at it. Nah. And we also have WCA. Okay, we put in what we know first. AB, Q is 0. Oops, should I have done that? Let me undo. Okay, let's see. QAB is 0. WAB is positive 480. And I know from first law of thermodynamics and the equation they helpfully give me in part A, plus Q plus W is equal to delta U. So 480 plus 0 is positive 480. Yay, Sudoku, line 1 complete. BC, WBC is 0. Did I change the color? My bad. Nah. WBC is 0. QBC, we don't know or miss. Okay lah, we park one side first, we don't know. So that's all we have. We know it's 1100, but I kind of don't want reserve my opinions on whether it's positive or negative first. Let me see what else I have. I have the work done from C to A, and this is negative 240. Negative 240 joule. Okay. What else? Let's think about this 1100 because we need to put it in. If not, very hard to complete the table, right? So we're going to go back here. and think about from B to C. Where is B, C? There, here we go. B to C. You see the temperature is dropping, right? So the internal energy is already going to drop. I write for you. I write. T from B to C decrease. This means delta U is negative. So far, so good. Let's go back to the table. This one is negative. This one is 0. You tell me, do you want positive 1100 or negative 1100? Surely it must be negative 1100 so that this one is negative 1100. So my thought process was this one is negative because the change in temperature from B to C decreases. So delta U from B to C is negative. And in order for this thing to be negative, this thing must also be negative because this one plus this one is this one. It's very tricky because you see here, they say transferred. And a lot of students will think, oh, transfer, show positive, because they didn't use the word remove. Okay, so when they say transfer, is IDK. Is it transferred to the gas? Is it transferred from the gas? Nani? Confusion. So you have to go and try to pick up some clues from the table or the graph. So the clue that I had was work done is 0. Okay, you must be able to deduce one. If they said when they set the question properly, we're talking about Cambridge, they will set the question properly, so you should be able to deduce. Work done is 0. Heat plus work done must be negative. So surely the heat is negative. And we know it's negative because the temperature decreased. Okay, I think we unlocked the whole thing already. Next one. This delta U must be 0. You total everything up. The delta U for A, B, C, A is 0. Why? Because there is no change in temperature. Temperature from A, B, C, A. The whole cycle. So, positive 480, negative 1100 plus delta UCA is 0. You can find delta UCA, right? Just bring over 1100 minus 480 will be 620. This is 620 plus. And then you can go back here and delta UCA is equal to Q from C to A plus W from C to A. So 620 positive is Q from C to A plus 240 negative. So Q from C to A will be 620 plus 240, that will be 860 joule. Finish. There is your 4 marks. So this part I like because it's a bit unpredictable and I need to think. But I also understand thinking can be a bit challenging when you are, doing question 2. So whenever you see a gas cycle and it's not obvious, pause, come back again when you finish the whole paper. They are not difficult. It's just that you need to think a bit, especially this part here. So a lot of students will put positive here and then they didn't check one. They just, okay, my answer look okay, then they move on and then they get 1 out of 4. Physics very hard. Okay, so sometimes there are little bits of sneaky tricks somewhere. Just make sure you are able to catch them by doing more questions and increasing your experience point. Okay, I think we are done. So what have we done? We have done a lot of gas questions from 2020 because 2020 is all gas questions. So just, and again, I will send out this printout into the meeting chat later. But the whole idea is we can ask questions involving the equation. These are the 5 equations. 1, 2, 3, 4, 5. This is a bit of a wildcard situation. And for specific heat capacity, this is the second most popular and it hasn't come out for an entire year. So who knows? Who knows? Who knows? Go try question. The gas cycle question also you should go and try. The thermometer one, maybe you're lucky it still won't come out lah. Okay. So go and try questions. If you want to find gas cycle questions, I will suggest a few, and then we will call it. I just randomly picked from past year one. Okay, so you could do try FM17 paper 42 question 2. And also recorded one that you may want to try first if you haven't viewed the recording. ON18 paper 41 question 2. This is recorded. So try a few to get familiar. May, June 15, paper 41, question 2. Okay, just to make sure they don't trick your feelings lah, especially with the 110 positive and negative one. Who knows, man? CIE is full of tricks up their sleeves. Okay, and I believe that we have we recorded this one? We have not. Okay. Another one that is a little bit tricky is an old one, ON10 paper 41 question 2. So this one may be a bit tricky, but try this 4. If you can try this 4 and you understand this one, then this question should be okay. Only 4 questions. One is recorded already. Go to. Okay. So I have suggested different things to try along the way. And the recording, as usual, will be up inside the meeting chat lah. Okay, that's it. Thanks for joining. Thanks for watching.